Hi everyone, my name is Sean and I am joined today by my team, Ryan, Kyle, Trevor, Cody, and Jordan. Our team will be discussing the Earth Lunar Transportation Network and the focus of the system, a lunar base. Programs like Artemis have brought a renewed focus on space exploration to the Moon and in the future, Mars. These international programs will have to develop a sustainable, scalable, and affordable transportation network to effectively carry out the missions. These networks consist of launch vehicles, space stations, landers, permanent settlements, and much more. The goal is to establish a permanent presence on the Moon, Mars, and beyond. With the scope of a transportation network being so vast, our group has focused its efforts on developing a lunar base, a key aspect of the early transportation network. The habitat will provide a safe, reliable, and cost-effective space for the astronauts to live, conduct experiments, and serve as a starting point for deep space missions. We will be exploring many concepts to see which best serves the needs of our stakeholders. The mission of this project is to develop a cost-effective, reliable lunar habitat that will facilitate a sustainable human deep space presence and serve as a hub for a transportation network between the Earth and the Moon. Although there are countless people involved in such a large international program such as this, we've identified three key stakeholders: government agencies, industry partners, and taxpayers. Our development process is also based on three assumptions we made. A launch vehicle is already developed, the initial mission is fully funded with the expectation of cost overshoot, and all external systems to the lunar base are developed. With the stakeholders in mind, we have identified several needs as seen on the slide. In general, government agencies are more concerned with crew safety, scientific research capabilities, and the duration of the mission, while industry is mostly focused on developing space economies, resource allocation, and profits, and taxpayers are mostly concerned with costs. We then use the stakeholders' needs to develop requirements for the lunar base. Although we could have made dozens and dozens of requirements for the scope of this project, we've identified 18 seen here and on the next slide. Here you can see the remainder of our requirements. This slide is mostly focused on the industry partners and taxpayer requirements, while the first slide was mostly dealing with government agencies.
My name is Jordan Soberg, and I'll be going over our ConOps for the lunar base. We determined 7 modules that were necessary to meet the requirements laid out earlier. First and foremost, the inhabitants of our base will require a space in which to live and keep storage of various equipment and supplies. This is referred to as Module 1 in the ConOps. Module 2 is the Environmental Control and Life Support System, or ECLSS. This module will have 3 subcomponents covering 3 main environmental concerns: water recovery, air revitalization, and oxygen generation. The base will also require a power system, in this case labeled Module 3, the Surface Fission Power System. This module will have 1 subcomponent, allowing for external power to be granted in buggy operation or emergency situations. Module 4 involves thermal control, and will require a heat acquisition system as well as a heat rejection system to allow for comfortable survival of the astronauts. Module 5 is the comm system that will connect to the Lunar Gateway comm system to allow communication back to Earth. In addition, this comm system will allow communication with local service elements such as buggies and rovers. Module 6 is the external payload and robotics capability, allowing astronauts to work with robotic partners to do science on the Moon's surface. Finally, Module 7 will be the Airlock with EVA suit compatibility, allowing for astronauts to transition between the Moon's surface and the habitat with ease. Next, on a broader scale, we can see how the lunar habitat will interact with the Gateway, using the Trans-Lunar Launch Pad. This launch pad will be optimally distanced from the habitat to ensure ease of access without jeopardizing the safety of the habitat due to accelerated ejecta. Finally, a mission to the Moon utilizing the habitat looks like this. First, the habitat will be dormant and maintain a power-positive status and minimal environmental controls to reduce complexity and the probability of failure. Then, upon scheduled astronaut arrival, the habitat will recommission to ensure habitable space for the astronauts. While the habitat is occupied, the habitat will run nominally, providing the uses outlined earlier in the ConOps. Finally, upon astronaut departure, the habitat will decommission to allow for reduced complexity once again. At this stage, the habitat will remain dormant until recommissioning during the next lunar mission.
Hello, my name is Kyle Alvarez, and I'll be going over the functional analysis for the lunar base design. Please feel free to pause at any time to read the diagrams. Starting off, we have the external systems diagram. Shows the external systems that will be interacting with the lunar base. The human land system transmits astronauts to and from the base. A lunar net to relay information to and from Earth. A lunar roving system to provide service level transfer for astronauts. And finally, a lunar cargo vehicle to relay supplies. In the middle of this diagram is a lunar base which provides habitation. A quick word on the legend: arrows in green are for information, blue are for physical matter, and red are for energy. So we can decompose the base's main function into 9 sub-functions which we will further decompose. First function, provide the crew with consumables, concerns providing food and water for the crew. Information on the consumable needs of the crew is passed on to these functions which seeks to satisfy these needs. Provide launch capabilities concerns the ability to track incoming vehicles as well as provide them the ability to land at the base as well as launch from the base. Conduct base operations concerns the day-to-day tasks of the base, such as collecting scientific data, conducting EVAs, processing information from the LunarNet, and providing living spaces for the crew. Collect and process materials concerns the ability for the base to collect materials from shipments or ISU activities and to process them into useful things. Monitor crew concerns the ability of the base to check in on the health needs of the crew. This information is then relayed to the other functions of the habitat, such as providing food and water. Monitor base's environment involves monitoring the radiation level, temperature, and air quality of the base's interior. Manage waste concerns the collection of waste from the other functions, storage of said waste, and the eventual disposal of waste. Finally, manage power concerns the generation, storage, and supply of power to the other functions based on their needs.
Hi, my name is Trevor, and I'm going to be going over our QFD and the house of quality that we created for our moon base. So if you look right here, we have the house of quality that we generated. On the left right here, we have 16 customer requirements that we defined earlier on in this presentation. We gave each of these relative weights from 1 to 5, with 5 being the most important and 1 being the least important, and then translated these into percentages to kind of get an idea of what we would think are the most important of the customer requirements. Now, up above at the top right here, we have 16 functional requirements. Now, these functional requirements are all practical requirements that we feel can best meet all the customer requirements. And if we go to the middle, right here, we have this matrice of relationships. So a dark circle here means a strong relationship between the customer requirement and the functional requirement. This upside down triangle represents a moderate relationship, and then these open circles represent weak relationships. If we go down to the bottom right here, we can actually see the metrics that we generated for each of our functional requirements. These metrics are based off of data you can get from NASA or other related sources, and they pertain to surviving in space. For example, we have maximum radiation exposure per year, maximum parts per million of carbon dioxide in the atmosphere. So really just scientific and life-pertaining metrics such as these. If we go down to the bottom of this house of quality, we do have one competitor that we compared our project to, that is the International Space Station. We feel that this is the closest analog. Generally speaking, our product did perform better than the ISS in pretty much every category, but we feel that this was a fair assessment because of the fact that our product is going to need to last longer and will be in a harsher environment than the International Space Station.
My name is Ryan Alcorn, and I will be taking you through our concept generation and selection process. Our team developed multiple concepts for each of the 7 modules that we defined in our mission ConOps. We then utilized weighted decision matrices to evaluate each of these concepts against our mission requirements. First, and most importantly, we developed 3 concepts for our habitable and storage volume. We considered using pre-built modules, building within lava tubes in the lunar surface, or 3D printing a habitat on site using lunar soil. This final concept won out due to its superior cost effectiveness and potential for iterative expansion. For the power system, we considered nuclear fission, solar, and geothermal generators. Nuclear fission was selected for its superior power generation and longest total operating life. For the comm system, we considered various radio frequency bands used by the Deep Space Network, as well as a newer laser optical technology. We opted for a hybrid system utilizing both of these technologies to maximize data rates while minimizing interference. For the Airlock/EVA suit system, we considered suit ports and single and dual airlocks. Ultimately, we again opted for a hybrid system featuring both concepts to maximize redundancy. For the environmental control and life support system, we considered mechanical filtering and regenerative life support. Once again, we chose a hybrid with both concepts due to its superior reusability. Both passive and active thermal control systems were considered for this module. We decided that a passive system would be best as it would reduce cost and complexity while also maximizing durability. Lastly, we considered both pressurized and unpressurized rovers to allow for astronauts to have superior mobility on the lunar surface. Once again, utilizing both types of rovers proved to be the best method in terms of safety and total range, even if it was the more costly option.
And to wrap it all up, my name is Cody Mancini, and I'm going to talk about the next steps in the development of our lunar base concept. With all the options of the main functions of the base weighted in our decision matrices, the best options for each function were revealed. Now, while these appear to be the best options on paper, there are clearly limitations to the choices and their implementation. First of all, a 3D printed base in low gravity has not been tested or verified. A more likely habitation timeline would be an initially small pre-built module, such as the components of the ISS, and use that as a kind of staging point to begin the 3D construction of the base and offer a solution to housing astronauts as they oversee the initial printing process, and therefore they can make the necessary modifications along the way. Similarly, nuclear power will also provide its own challenges, despite appearing like the best option. While it has the highest capacity for power generation, it's going to be an extremely delicate and costly process to ship a reactor and fuel to the moon. Solar panels and batteries are a simply workaround in the meantime, but they are substantially limited by 2-week day-night cycles on the surface of the moon. And as the electrical needs of the base grow with time, these would not prove to be a sustainable option. Now, with the final concept of the base in place, we can begin to talk about the cost. As with any major breakthrough in space technology comes an increasingly complex design process. With Project Apollo, at peak, there were thousands of contracts to outside companies and up to 400,000 people working towards the program's goal. Same with the ISS's construction. These are incredibly complex systems that take years to develop and are therefore very difficult to establish at cost. While NASA may have the means and replicas to come up with cost estimates, we can never hope to go into the detailed cost estimates for this plan. So we've theorized here the next steps for a committee whose mission could be to do just that. Currently, NASA has the Artemis plan, their plan for lunar habitation, set for $20 to $30 billion up front, with about $5 billion per year in sustaining it. So that's going to be our initial goal as well. Alongside cost comes the actual development plan for the project, dedicating R&D, production, finances, etc. With that said, we've laid out a plan for how this endeavor could begin to be shared with industry and the bids and prototypes from around the world that would begin the final development phases. Looking back to the 3D printing and the nuclear reactor, these are technologies that are going to require extensive research and testing before they can be implemented on the lunar surface. These are going to be tremendous engineering challenges to be solved in safely transporting nuclear payloads, as well as the crew's initial habitat and printing equipment. As the lunar base looks more and more promising in the coming decade, it is the next monumental step in human space exploration. Once a base on the moon has been proven, it paves the way to habitats on other planets, further developing our scientific and engineering capabilities. I know all of us over at Hard Dirt Technologies are thrilled for the future of human spaceflight exploration and want to thank you for tuning into our development of the lunar base concept. Thanks.